This is Neil Pitwari. I'm hoping that the example that I do in this video segment is enough to remind us about probability, and in particular, how to calculate the probability of error in a binary communication system. A learning objective of this course is computing the probability of error, and so I'm hoping that this example will remind you of all those things that you remember from your probability course about probability density functions, CDFs, PDFs, and conditional probability. So in this example, I'm going to consider a binary PAM system that has two possible symbols. Those symbols are going to have values of -3 and +3. That is, when we want to send a 0 bit, we send S0 of t. When we want to send a 1 bit, we send S1 of t. Okay, so S0 is -3, S1 equals +3. In this example, we're going to study a receiver. If X, our received voltage value, is less than 0.5, then I'm going to decide that S0 was sent. And if it's greater than or equal to 0.5, I'm going to decide that S1 was sent. And that's how we're going to decode the information that was sent. I know that I've said that you typically draw the threshold halfway in between the two symbols. But in this example, I'm going to pick a different threshold because we do need to know how to calculate the probability of error for any arbitrary threshold in order to study what happens as a function of that threshold. So it is important that we be able to calculate these probabilities. We're going to assume that X is equal to S sub 0 plus some noise W. And the noise is Gaussian with zero mean and variance sigma squared of 4. The questions we're going to ask are as follows. Our first question is about the conditional probability of correctly deciding that S0 was sent, given that S0 was in fact sent. What we're going to do to solve that is that we're going to have to consider this probability, the probability that S0 is received, given that S0 was sent. And this is the kind of the words that I'll use to describe this probability. The vertical line separates the event that I want to know the probability of and the event of the given information. I'm given that S0 was sent, so that goes after the vertical line in the probability statement. And this translates into something about X. That is the same thing as saying that X is less than 0.5, because I've said that we decide that S0 is received when X is less than 0.5. And this is given that S0 equals -3. That is the condition of what happens when S0 is sent. We send a -3. And we know that X is equal to S0 plus some noise. So what this translates into is that X can be replaced with -3 plus W. Let me just solve for W on one side here. We've got W is less than 3.5. And it doesn't really matter at this point what S0 is. We've included all of the given information on this side, so we don't actually need to continue to write down this event. And this is a statement about a random variable W that has a Gaussian distribution with zero mean and variance 4. The way that we describe random variables is with their cumulative distribution function. So the CDF, it's written like this: F capital W in subscript, lowercase w in the parentheses, is equal to the probability that that random variable is less than some value little w. In this case, we're talking about FW of 3.5. Another thing to know about the CDF is that the CDF is an integral from -infinity to the value that we have here, this lowercase w, of the PDF, the probability density function. And here I'm going to put in a dummy variable so that I can do the integral, and the integral will get rid of that u and replace it with the little w in the answer. Here, what we're talking about in terms of the value of 3.5 would be to plug into that integral. 3.5 instead of little w. I'm going to take this around here, is a Gaussian PDF. So it has this function for all u, all values of u. We take that value of u, we subtract the mean, and we square it. We divide by 2 times the variance, and we put all that in an exponential, and we multiply by the constant 1 over the square root of 2 pi times sigma w squared, the variance. In this case, the variance is 4, and the mean is 0. So that would be the form of our function. The only problem is that we don't have an analytical function that allows us to integrate this exponential of minus u squared. So what we do instead is we try to use the CDF of a standard normal. We call that phi of x. We define as the integral from minus infinity to x of 1 over the square root of 2 pi times 1 times e to the minus u squared divided by 2. And this is the CDF, cumulative distribution function, of what's called a standard normal. That is a random variable that is Gaussian with mean equals 0 and variance equals 1. That's standard normal, mean 0, variance 1. I'll show you that we can calculate this in MATLAB pretty easily. Once we've defined this function, what we're going to do is we're going to convert our w into a standard normal random variable so that we're able to apply this phi function and use the phi function to get our answer. We're also going to define a q function, which is the opposite the phi function, because it is also very common, and it's going to be the integral from x to infinity of the same standard normal random variable. We had this function here. The probability of the w is less than 3.5. I'll copy that here. What we're going to do to convert w into a standard normal, there's always 2 steps. 1, subtract the mean, and 2, divide by the standard deviation. Not the variance, but the standard deviation. These 2 steps convert a regular Gaussian random variable into a standard normal random variable. So in here, I'll show that in 2 steps. I'll subtract the mean. Here it's 0. What I do then is I divide by the standard deviation. The standard deviation here is the square root of 4. So I put 2 in the denominator, or I get, because this is a probability about a standard normal random variable, it is essentially this integral with the little x of 1.75. So what I then do is I get to just write this, phi of 1.75. And I can type it into MATLAB, and I get an answer that this is about 0.9599. A 95.99% chance that I'm going to correctly receive my bit of 0. That answers this question: what is the probability that S0 is received if S0 was sent? Second question is going to be, what is the probability? What is the conditional probability I receive S1 given that S0 was sent? It's the same question as before, except that instead of asking about receiving an S0, I'm asking about now receiving the wrong symbol, the S1 symbol. So if it was a probability of this 0.9599 that I got the correct symbol, then it's going to be 1 minus that for the probability of receiving the wrong symbol. I could have also started this problem a little bit earlier and said, what is the probability? I've written this as the probability that S1 is received. S1 is received whenever x is greater than or equal to 0.5, given that S0 is equal to minus 3. And I could convert this in the same way that I did before. And this would result in, because this probability is a standard normal random variable greater than some threshold, that is our definition of this Q function, that then I can just plug into the Q function that 1.75, and when I plug that into MATLAB, it gives me the same number, 0.0401. Okay, so that's our answer for part B. Our question in part C is, what is the probability that 0 is received if S1 is sent? This is the probability that x is less than 0.5 because I'm asking for the probability of S0 being received. Given S1, which was positive 3, and I would go through this same exercise, convert this into a question about W, to convert this into a question about a standard normal random variable, and then to convert it into a phi function. So I would get a phi function because, again, I'm asking for a standard normal random variable less than some number, and its probability is given by the phi function. Whenever I get that less than, I convert it into a phi function. Whenever it's a greater than, I convert it into a q function. So the phi function at minus 1.25, I plug that into MATLAB, and I get this value, 0.1056. Okay, just remember that this is not equal to the probability that S1 is received when S0 is sent. They're not equal probabilities of error here. It's also not the complement of that first answer he had, the 0.9599 probability. It's not the complement of that. We can't just do 1 minus because we know the probability that S0 is received given S0 is sent. So the final question, we've computed the conditional probabilities of error, that is the probability I get the wrong symbol at the receiver, given that S1 is sent and given that S0 is sent. But now I'm going to ask, what is the overall probability of error? And here we're going to assume it's equally likely to send a S0 symbol as an S1 symbol. So what we need to use to solve this problem is we need to use the law of total probability. And in this case, it tells us that we can find the probability of the event we want, this error event, by intersecting it with the probability of error and S0 sent, and the intersection of the error with the S1 sent event. And this is because S0 and S1 are a partition of our entire space. That is, one or the other is going to happen. There's nothing else that could happen. Once I've divided up my probability into two parts here, I can write this intersection of error and S0 sent, these two events, as the conditional probability of error given S0 sent times the probability that S0 is sent. This is how I define the conditional probability as the joint probability divided by the probability of S0 sent. So this product becomes the joint probability. These probabilities are both 1/2. So I'm going to have 1/2 times this probability of error of S0 being sent. And that was this answer for part B. It came out to 0.0401. And the probability of error given S1 was sent. This answer to part C, the 1056. So I get 7.28% chance of error overall when I run this communication system, sending zeros and ones equally likely. Hopefully this has made you recall some of the properties of probability, the law of total probability, the use of conditional probability, and doing integrals to come up with the cumulative distribution function from the probability density function. And in particular for Gaussian random variables, using a kind of a new function named phi of x or q of x as the CDF or complementary CDF of that standard normal Gaussian PDF. And that's all we have for this example.